folks. It's my honor to introduce Dr. Watson. Dr. Watson, I'll turn the Zoom over to you so that you'll be able to share your screen in a moment. But before I do that, let me start the recording. Great. Okay. Looks like we're already started here. And let me do a quick introduction to Dr. Watson. So Dr. Watson is a board-certified physician, principal of NeuroSleep, director of the Harborview Sleep Clinic, co-director of the UW Medicine Sleep Center, and a UW professor of neurology and past president of the American Academy of Sleep Medicine and American Board of Sleep Medicine. So we're truly honored, Dr. Watson, to have you. We thank you in advance for your time on behalf of our entire ecosystem, and I'm really eager to hear what you have to say about sleep medicine. So with that, and feel free to add any other information by way of introduction. I will turn it over to you. So I'm going to, Dr. Watson, I will enable you to share.
All right. Can everyone hear me okay? Are we good here? Let me get my video. All right. Let's see. It's saying I can't start my video because the host has stopped it. For some reason, I haven't seen that before. Any ideas how to solve that, or shall I just go on and proceed?
Yeah, I think you were able to see your presentation just fine. I see your intro slide, sleep and human longevity, so we should be good.
Okay, all right, that's fine. There won't be any video, so sorry about that, folks. But yeah, it's my great pleasure to be here today to speak with you about, I think, a very interesting topic. And it's interesting. The zeitgeist for the longest time has been, I'll sleep when I'm dead, kind of thing. But what we're learning is that, in fact, you sleep to live. And I hope that at the time, at the end of this talk, you'll have a better understanding of why I would make such a bold statement. All right, so I really want to start off here by pointing out that healthy sleep requires these 5 elements, and so we should all seek to have these elements in our life. So adequate duration, and I'm going to talk more about that later. What exactly that means, but so I'll sort of go past that right now. But short sleep is not good for you and is problematic. Regularity, it has to happen kind of on a regular basis. There has to be a regular bedtime and a regular wake time, and that has to be consistent from night to night. Timing is important. Sleep must occur when it's dark out. Well, not must, but it's idealized. We are, through millennia, designed as human beings to sleep when it's dark out and be awake during the day. And we know that, for instance, people that are shift workers, that makes up about 20% of the working population right now, they have all kinds of problems because they're trying to sleep during the day and be awake at night. Problems with cancer, breast cancer, colon cancer, prostate cancer, issues with cardiovascular disease as well, depression and other things. So timing is important. Quality has to be good. And that's kind of a thing that's sometimes a little bit hard to put our finger on exactly what that means. I think we know it when we have poor sleep quality. We may not know it as much when we have good sleep quality, but the sleep needs to be of good quality. And then lastly, the absence of sleep disorders, or if sleep disorders are present, they're adequately treated. And so what I'm talking about there is obstructive sleep apnea or sleep disordered breathing, central nervous system hypersomnias like narcolepsy, insomnia, circadian rhythm, sleep disorders, restless leg syndrome. So all of these things have to be aligned. They have to be present for a person to have healthy sleep. So this was a really interesting study that was done a number of years ago in Alan Rechthoffen's lab, where basically this was a total sleep deprivation experiment in rats. So you can see you have a brown rat and a white rat on this platform with a glass partition between them. Now imagine the platform is actually in a barrel of water, okay? Now, both of the rats have their EEG being monitored to determine when they fall asleep. However, only the white rat, every time they began to fall asleep, the platform would rotate, the glass would knock both rats into the water, and then they would have to swim around to not drown until they found the platform again and could climb back on it. So this was a total 100% sleep deprivation experiment in the white rat and a sleep deprivation experiment in the brown rat, but not 100%. And what you can see is that essentially the totally sleep deprived rat, despite increasing caloric intake dramatically, was losing weight. They were started to lose their hair. They lost the ability to control their body temperature. Their plasma thyroxine levels got out of whack, and ultimately they died after about 4 weeks. The brown rat that was not 100% sleep deprived did survive, and then once it was put back on an ad lib schedule, it went back to normal. The point here is that sleep is absolutely essential to life. Now, and if you don't get it, if at all, at least in this experiment in mammals, it's not compatible with life. So as I go through my talk here, I just want to make sure that the language we speak and some of the things that we need to understand collectively about sleep are present here. So yeah, when we measure sleep, we do it through electrodes that are placed on the head, where we monitor the electroencephalogram or the EEG of the brain. And so sleep is essentially divided up into REM and non-REM sleep. And non-REM sleep is divided into stage N1, N2, and N3. Now, if you look at N1 at the top there, you can see the EEG, that's a low voltage mixed frequency EEG. The eyes are represented in blue, and there's not rapid eye movements. There might be a little bit of slow rolling eye movements, and you can see the chin tone, the EMG, is kind of high. That's going to make up about 5 to 10% of your night, and that's how you're going to enter sleep. If we go to the right and we look at stage N2, you can start to see those fast 14 hertz sleep spindles, and then those big slower waves that represent what we call K complexes. And these are brain phenomena that are associated with N2 sleep. That's going to make up about 50% of your night of sleep. And then lastly, you have stage N3, or not lastly, but from a non-REM perspective, lastly, stage N3, which is these high voltage delta waves, 75 microvolts or higher. They're slow, about 2 hertz or so. And that's going to make up about 15 to 20% of your night's sleep. And then you have REM, which is unique. It's different. It's the stage where dreaming typically occurs, although not all the time. And you can see that in the blue, that deflection is a rapid eye movement that's associated with it. And then also, if you look at the chin tone at the very bottom, that is reduced because our bodies paralyze our skeletal muscles when we're in REM sleep so that we don't act out our dreams. And when we do, that's a disease called REM sleep behavior disorder, which we often see associated with neurodegenerative disease. So these are the stages of sleep, about 80% in non-REM, about 20% in REM. If you look at the non-REM stages, stage N3 is a sleep stage that we preferentially recoup after a period of sleep deprivation. So that, along with the fact that hormonal release is associated with that, suggests in some people that that may be the most important sleep stage, although that is debatable. Here we have something called a hypnogram that we utilize in sleep medicine. At the top is a normal hypnogram, and you see time at the bottom and then wake, REM, N1, N2, N3. And so at the top, you can see in a normal individual, they have consolidated sleep. They enter sleep in non-REM. The majority of the N3 sleep is occurring in the first third of the night. Then if you look at the REM sleep, the majority of that's occurring kind of in the last half to the last third of the night. So this is kind of the natural ultradian rhythm of sleep happening in a healthy individual. By contrast, below that is a patient with a disease called narcolepsy, which is a deficiency of a neuropeptide called orexin in the hypothalamus that causes sleep state instability between wake and sleep. And so you can see here, it's almost like that consolidated sleep got chopped up and spread out over a 24-hour day. And you can also see REM sleep happening earlier in the sleep period than you see in the healthy individual. And so that's a picture of sleep disturbance, of sleep happening during the day when it shouldn't happen and you don't want it to happen necessarily, and not happening as much at night when you do. So when we talk about sleep, we also have to talk about circadian rhythms, because these things are tightly linked. And here's an example, or a one component of what we call the two-process model of sleep. So the circadian rhythms are controlled by process C, which is an area in the hypothalamus called the suprachiasmatic nucleus. And essentially, what happens here is that light goes into the eye, and it stimulates some cells in the retina that are melanopsin-producing cells. Those cells then stimulate the SCN, which through a multisynaptic connection suppresses melatonin secretion from the pineal gland. And that keeps us awake during the day, this kind of activating wakefulness signal generated by the SCN. Now, this is entrained to a 24-hour day, mostly by light-dark cycles. So your exposure to light is the single, by far, most important thing that will entrain your circadian rhythm to a 24-hour day. There are other things that help entrain as well, however. And so those are called Zeitgebers, which are these environmental events or agents or cues that provide this stimulus setting for resetting a biological clock. And so, like eating regular meals at regular times, having a consistent work schedule, the timing of your social interactions and regular exercise, your bedtime ritual, all these things are important from a circadian health perspective, from a sleep health perspective, because the body needs to be entrained and it needs to know what comes next. And so I can't tell you how many times I see people with insomnia leading incredibly erratic lives, and there's no pattern to things. There's no pattern to bedtimes or wake times. There's no pattern to when they interact with people. There's no pattern to when they eat their meals. There's no pattern. And the body needs patterns in order to be able to sleep effectively. Then there's this homeostatic drive. Okay, so on the bottom is that circadian alerting signal, the process C that I just described for you. At the top is what's called the homeostatic drive, or process S. And basically what that means is the longer we stay awake, the greater our drive to fall asleep. Okay, so you can see over the course of the day, the homeostatic drive builds up and the alertness signal also grows to oppose that, to allow us to remain awake in the face of a high homeostatic drive to sleep in the early evening hours. Okay, so and this line here kind of represents the balance between these two factors. Now, there is a natural dip in our circadian alerting signal around 2 to 3 in the afternoon. Some people take it, or some cultures take advantage of that to take naps and things like that. In other cultures, it's where the line at the coffee store is the longest, around 2 to 3 in the afternoon. The caffeine industrial complex is what I call it, but they take advantage of this little dip. But the dip is there nonetheless. It's not a postprandial thing. If you feel a little sleepy around 2 or 3 in the afternoon, that's normal human physiology, okay? But what happens here then, this buildup of this homeostatic sleep drive is likely a buildup of the purine nucleoside adenosine. Now, if you think back to biochemistry, adenosine triphosphate is the power pack of the body, and it gets dephosphorylated to generate power. So it goes from ATP to ADP to AMP to adenosine. So it's adenosine buildup represents the burning of all that energy throughout the course of the day. And we know when that builds up in an area of the brain called the ventrolateral preoptic nucleus, that hastens or brings sleep onset about. But really, so we have these two balancing forces here, and then something happens. It gets dark out. When it gets dark out, okay, there's no more light stimulating the suprachiasmatic nucleus. The suprachiasmatic nucleus is no longer suppressing melatonin secretion from the pineal gland. Melatonin is then secreted, which goes out and suppresses the circadian alerting signal, and sleep happens. And that's how we can go from being awake at night to being asleep at night fairly quickly. Then as we sleep, the homeostatic drive is slowly but surely reduced through the process of sleep, and the circadian signal also reduces to allow us to remain asleep. Then when it starts getting light out in the morning, process C comes back on in the face of a low process S, and we wake up and hopefully feel refreshed at that point in time. So that's what's called Borbély's two-process model of sleep. Process C alerting us, process S trying to put us to sleep, light being crucial, melatonin being crucial. All right, so let's pivot, beyond kind of the general discussion and language into some specific things related to the issue at hand, which is the association between sleep and human longevity. So about 4 or 5 years ago, some seminal studies were published that identified what is now called the glymphatic system in the brain. And so here you can see, if we look at, what makes up the volume of the brain inside your skull, you have about 10% of it is blue, that's cerebrospinal fluid. You have 10% that's going to be blood, that's in red. And then the rest of it, 80%, is really the brain parenchyma. But that's broken down between about 60 to 70% intracellular fluid and about 12 to 20% of interstitial fluid. Now, when we go to sleep at night, and particularly in stage N3 sleep, our brain contracts just a little bit. And what it does is it opens up this glymphatic system that then allows the brain to flush out all the byproducts of a day's worth of neurotransmission. And so that's shown here. In this figure, we have a young individual at the top, an older individual in the middle, and somebody with Alzheimer's disease at the bottom. So at the top, you can see that the CSF enters the brain parenchyma through the periarterial pathways with that red arrow coming down. And then essentially, it goes through these aquaporin receptors, which are the little blue dots, into the interstitial space where these proteins, beta amyloid and other metabolic waste is flushed out towards the venous side of the system and then out of the brain, okay? That's the way it's supposed to work. That's the way it does work, okay? As we age, glymphatic function is reduced a bit, and that's possibly due to the astrocytes here that are purple becoming reactive, and the aquaporin transmembrane proteins getting depolarized from the vascular end feet into the parenchymal processes. So, there's some neurobiological issues going on with normal aging that makes this process a little less effective. But then we get to a disease process with Alzheimer's disease at the bottom. And you can see, in the perivascular space of penetrating arteries, they're subject to accumulation of beta amyloid shown in yellow. And so you can see the red arrow coming down on the side, all the beta amyloid clogging things up. And that ultimately is going to result in beta amyloid aggregation, which we know is a key step in the pathogenesis and progression of Alzheimer's disease. So different ways, thinking about this glymphatic system, not just neurodegenerative disorders, but traumatic brain injury can affect the glymphatic system. Stroke can affect the glymphatic system. Lots of neurological disease processes can affect this, and that can have untoward impact on brain health. Okay, let's talk a bit about telomeres. So telomeres are these little protein end caps on chromosomes that are critical to maintain chromosomal integrity. So, basically they protect the ends of chromosomes from progressive degradation and ensure that the integrity of the chromosome is maintained. And they prevent DNA repair systems from mistaking the ends of the DNA strands for a double-stranded break. All right. Now, so essentially what we know is that telomere shortening is associated with oncogenic transformation, so cancer development, apoptosis, which is cell death, or senescence, which is just a cell in kind of a suspended state. And so progressive shortening of telomeres is something that's seen with aging, and it can be problematic. So this can have untoward impacts on health and lifespan, and shorter telomeres are associated with an increased incidence of diseases and poor survival. Now, this was a really well done research study that looked at the association between various sleep parameters and telomere length and shortening. And what you can see here is that you have sleep duration and sleep efficiency. As sleep duration goes down, telomere attrition goes up. As sleep efficiency goes down, telomere attrition goes up. The telomeres are burning faster. They're getting shorter faster when you're sleeping shorter, or the amount of time that you're trying to sleep, you're less successful at it. Sleep latency, the amount of time it takes you to fall asleep, did not show an association here. But they also had subjective measures of sleep quality and latency, duration, and efficiency, and also showed that subjective reports of people that were poor, had worse sleep quality and worse sleep efficiency, subjectively also had a faster LTL shortening. So it seems to show that suboptimal sleep, and again, this story is continuing to be told. But preliminary research is suggesting that, suboptimal sleep in a number of different ways predisposes to more rapid telomere shortening. Okay, let's pivot to mitochondrial DNA. We know most of our DNA is in the nucleus of cells, but some is in the mitochondria and is mostly involved in oxidative phosphorylation. But what we know and what we've learned about mitochondrial DNA and the copy number, which is the amount of it that's in the mitochondria, if in peripheral blood cells, it declines with age and is associated with general health among the elderly. So if you have a lower mitochondrial DNA copy number, you have poorer outcomes in terms of cognitive performance and physical strength, self-rated health, higher all-cause mortality, and then subjects with higher mitochondrial DNA copy number. And so, it suggests that a higher copy number of mitochondrial DNA is associated with better health and survival among the elderly. And we did some research a few years back to really investigate this. So we took monozygotic twins, identical twins, they're genetically identical, and that were sleeping different amounts of time, that we objectified through what's called wrist actigraphy, which is a little device that you wear on your wrist, and it tells whether you're moving or not, and it's an indirect measure of sleep. And we were specifically recruited twins where one twin was sleeping a quote unquote normal amount at 7 to 9 hours, and another twin was sleeping a short amount at less than 7 hours. And then we looked at peripheral blood leukocyte DNA, mitochondrial DNA copy number. So the mean within pair sleep duration difference was quite robust. It was an hour and a half. So there was big differences there. And what we found was that for every 1 minute decrease in this actigraphy defined sleep duration was associated with a decrease in mitochondrial DNA copy number of 0.06. And then likewise, a 1% decrease in actigraphy defined sleep efficiency was also problematic, as shown here. So, I think that this is some research that we did trying to get at this a little bit more. One thing to understand about mitochondrial DNA copy number in disease is that it's not an absolutely clear story. In some human diseases, copy number would go up, in others it goes down. So a lot of the story is yet to be told. Some of that variability might be related to the way that the assays are done, or it just might be very complex. So this is a story that continues to need to be told, but there's a suggestion here anyway that short sleep reduces mitochondrial DNA copy number and that that's associated with poorer health and aging. Okay. All right. I want to talk a little bit about waveforms here. We in this country do up to 25 million sleep-wake EEGs for the purposes of evaluating people for epilepsy or people that have had traumatic brain injuries or neurodegenerative diseases. We do about 4 million polysomnograms, which are overnight sleep studies where we're also collecting waveforms from the brain and we collect the EKG, we collect respiratory waveforms. Waveforms are really everywhere. And for the longest time, we would analyze this data visually just by looking at it. Like sleep is scored in 30-second epochs. And if 50% or more of that 30 seconds there's sleep, that 30 seconds is scored as sleep. Okay. Why, you might say? Well, back before everything was digitized, people ran sleep studies on paper, and the paper that you would flip would collect 30 seconds of data. So there wasn't any real reason behind it. But we're way beyond that now, and we're collecting lots of data. But what we're realizing is that the situation is much like this picture. So I'm in the Seattle area. This looks like a temperate rainforest to me out in the Olympic Peninsula. That might be my perception of this looking at a sleep EEG with my own two eyes and trying to draw conclusions. Well, what we're learning is that artificial intelligence is allowing us to look at the sleep microarchitecture. And by virtue of that, we see things that have been there the whole time, but we haven't been able to realize. So for instance, in the middle, you can see it looks like there's a panther. There's another big cat on the other side. There's an elephant in here. Some of you may have seen the tree sloth. There's an orangutan. There's all kinds of animals in this picture, and that heretofore previously we wouldn't be able to see. So artificial intelligence is bringing insights into the human EEG that we didn't have before. And one of the things that I'm most excited about that's going on is that we're able to determine what's called brain age from the EEG. Now, previously, people would look at consecutive MRIs or MRIs performed in an individual separated in time to look at the volume of various areas of the brain to come up with a brain age measure. But that's a static measure. The EEG is a measure of functional impairment or ability of the brain. And so, what we're looking at is there a difference between the chronological age of somebody and the brain age that we determine through this deep convolutional neural network that we apply to the 6 EEG and the 2 EOG leads that we get in an overnight sleep study. And there is data, the MRI data anyway, showing that the brain age is associated with Alzheimer's disease, schizophrenia, epilepsy, traumatic brain injury, and all the other diseases there that you can read for yourself. So here's the panel on A is showing you brain age plotted versus chronological age if you just look at sleep macro architecture that we would measure, that humans would measure. And you can see the mean age difference, which is absolute, was 23 years. So it's quite spread out. The red line is where brain age and chronological age exactly match. Then in panel B, it's the same thing, except we're looking at sleep microarchitecture, and you can see it tightens things up quite a bit with a mean age difference of 7.8 years. But what I want to point out, something that's really cool here, is these figures. So if you look at it, the rows are people, the top row, chronological age of people in their 20s. The middle row is chronological age of people in their 40s, and the bottom row is a chronological age of people in their 60s and 70s. And at the top is the hypnogram that I showed you before for that individual, and then below that is the spectrogram which is looking at the probability distribution of different frequencies in the brain. And what you can see is that some of these people, if you look at the diagonal, for instance, some of these people have a brain age that's way younger than their chronological age. And you can see on the converse, some people have a brain age that's way older than their chronological age. And if you look at the frequency in hertz at 15 in the spectrogram, in those with younger brain age, you can see that there's those well-defined areas at the top in light blue. Those are sleep spindles. Those are the things that characterize stage N2 sleep. So it's just kind of showing you that, like, you can see that tighter organization of sleep spindles in those with the younger brain age compared to chronological age versus those with the older brain age compared to their chronological age, where it's just kind of a smear. There's not really good differentiation. And there's there's some proof here that this actually is associated with the things that we believe would be bad for the brain in the direction that we would assume it would be. So, for instance, brain age, as N3 time goes down, brain age goes up. As stage N3 percentage goes down, brain age goes up. As sleep efficiency and total sleep time go down, brain age goes up. As N2 time goes down, brain age goes up. And then you look at something like the respiratory disturbance index, which is a measure of sleep apnea. As that goes up, brain age goes up. As N1 sleep goes up, brain age goes up. N1 sleep should only make up 5-8% of your night. You enter sleep in N1. If you're spending a lot of time in N1, you have poor sleep quality. And then wake time after sleep onset obviously is not good for you. And if that goes up, your brain age goes up as well. And if we take this one more step further, you can see here in these histograms that if you were looking at depression, diabetes, and hypertension, and the brain age index is on the x-axis and the density is on the y-axis, and you can see the kind of tan color is those that have these diseases, and the green color are those individuals that don't. And so you can see, compared to individuals that don't, those with depression, diabetes, and hypertension, their curves are moved to the right towards a higher brain age. And so the difference on average, I think here is about 3 to 4 years, roughly, for each of these disease processes. So this is kind of, once again, showing that this is a meaningful way for us, I think, to kind of measure the health of a person's brain. All right, I mentioned earlier this notion about sleep duration. It's one of the 5 things that have to be present for healthy sleep. Well, how much? It really, it's a very interesting debate in sleep medicine. You have some people that take the optimal dose approach, which in this figure here is shown by the light gray. And you can see what we have on the x-axis is the duration of sleep, and on the y-axis, the odds of incident disease or weight gain. And so these people say, hey, there's an optimal dose of sleep. And if you get less than that or more than that, that's bad. Then you have other people that say, I think sleep is linear, and that, sure, shorter sleep is bad, but there's no amount of additional sleep that's necessarily problematic. Sleep in and of itself can't be bad for you, okay? I fall more in that camp myself, because if you look at the all the data that's out there, all the experimental data in humans and in animal models, there's a lot of data showing that if you sleep restrict, particularly below 5 hours, your body doesn't handle glucose very well, your cardiovascular system gets out of whack, your ability to react and think clearly becomes affected, your immune system is impaired. I mean, on and on and on. But there is essentially no experimental studies where you extend sleep in animals or humans and show any of those untoward effects. So you might say, well, Dr. Watson, then why is there this U-shaped belief? And it's because a lot of epidemiologic studies seem to show an association between longer sleep and some poor health metrics. But from my perspective, what I think is going on is that when people get unhealthy They live a more sedentary lifestyle, and they're going to self-report more sleep because of that. And that's why there's an association. Not that there's a problem with the sleep necessarily per se. So that would be kind of my thinking and approach to this after having spent a lot of time looking at this literature. I do not think sleep can be bad for you. And in fact, if somebody's sleep satiated, you can't force them to sleep longer than what their body needs. Like, you can get somebody completely sleep satiated, but you can't go beyond that, because you just won't fall asleep. So I was led a consensus conference a number of years back. We looked at all this data and concluded, from a public health standpoint, for adults should sleep 7 or more hours per night on a regular basis to promote optimal health. Now, nobody sleeps every minute that they're in bed, right? No, people don't. There's no such thing as a sleeping beauty. Okay. So we all have some time where we're awake, either before we fall asleep or in the middle of the night. So if you want to get 7 or more hours, you probably got to spend 7.5 hours in bed, 8 hours in bed, something like that. So that's just another thing to think about. And then lastly, of course, the amount of sleep that any given individual needs can be variable. It's highly genetically penetrant. If you want to know how much sleep you need, take a vacation, sleep vacation, whatever you want to call it. Go to bed when you start feeling tired at night. Wake up when you feel refreshed in the morning. Do that for 2 or 3 weeks. And then whatever that duration is, that's how much sleep your body needs. But in order to do that little mini experiment on yourself, you have to listen to your body. So if your body starts getting drowsy at night, go to bed. And if you in the morning, don't set an alarm, just wake up spontaneously. And that's how you'll learn what your sleep need is. And when we talk about sleep duration, one of the reasons we did this consensus conference was for the CDC to be able to do some research with a lot of the data they collected, including this behavioral risk factor surveillance data. So here you can see this is the percentage of adults who reported greater than or equal to 7 hours of sleep for 24-hour period. So darker colors are better. All right. Look at this. So you can see in the middle of the country, sleep is better, and then kind of on the East Coast, not as good. Now I'm going to lay on top of this another CDC figure that looks at obesity, prevalence of self-reported obesity. What do you see? You see a lot of the areas where people were sleeping less are the areas that are also obese. Okay. And why is that? Well, did another twin research a number of years ago, which this is called a gene environment interaction. And the figure is what kind of tells it all, where we're plotting sleep duration by the proportion of variance in the body mass index. And this stuff is very complex statistically, but the bottom line that you can see there is, as we sleep less and less, we're turning on genes related to obesity. So obesogenic genetic drivers get turned on when we sleep less. And that was the takeaway finding from this study. So in conclusion, and we're going to open it up for questions here. I talked about the requirements for healthy sleep, adequate duration, good quality, regularity, happening at night, and absence or treatment of sleep disorders. And so as you go through your life and you think about that, think about those components. Touched on Rex Stoffin's classic animal study that showed in the totally sleep-deprived rat died after about 4 weeks of time. So sleep is absolutely necessary for life in mammals. We looked at the hypnogram and the various sleep stages and REM and non-REM sleep and talked about that. We went through what's called Borbely's two-process model of sleep, where you have this process C and process S that oppose each other. There's a circadian alerting component. There's the buildup of adenosine the longer you stay awake. These two processes oppose each other and work together. And the key moment in being able to fall asleep and wake up is it getting dark out. So one piece of advice for people is start to dim the lights in your house as you're starting to go towards later in the evening, towards bedtime. Okay, that's one of those habits that can start getting your body ready for bed and start getting that melatonin secreted. Talked about the importance of the glymphatic system, that it typically gets turned on in N3 sleep. The brain contracts a tiny bit. It opens up, all of these interstitial space pathways where the byproducts of a day of neurotransmission can get flushed out of the brain, including beta amyloid, and that this may be one of the processes involved in neurodegeneration. Talked about the complicated nature of mitochondrial DNA and sleep, but at least in the twin study showing that shorter sleeps associated with reduced copy numbers associated with poorer health in some instances. And then also that, bad or insufficient sleep, reduced sleep duration, low sleep quality can potentially increase the burn rate of telomeres, which can be oncogenic and associated with disease processes. Touched on brain age and sleep and how we're beginning to learn through sleep microarchitecture that we have a robust measure of brain age. And, it's yet to be determined if you change your healthy habits or you treat diseases, if your brain age can recover. And that's something that we're excited to take a look at down the road here. Sleep duration, how much is enough? What happens when too little? Talked a bit about that. 7 or more hours for adults is a general recommendation, but of course, everybody's unique. And I told you how to figure out what your number is. And then just, looking to the future, I think really as we move more towards personalized medicine, and I know human longevity is a leader in this area, I think we're going to bring a lot of this information to bear, at least from a sleep perspective, to try to optimize things in order to optimize human health and longevity. And so with that, I appreciate everyone's attention. Although, hold on a second, I do have one more slide here. You might have remembered the Michael Jackson trial. So Michael Jackson died because he was being given propofol, which is a general anesthetic, to ostensibly help him sleep. But, just because your eyes are closed, you're unresponsive, and you're recumbent, doesn't mean that your brain is doing all the things that it needs to do to be asleep. Okay. And that was the problem here. Like Michael Jackson could take propofol and then 8 hours would go by, but he wasn't sleeping. Okay. And so I think it's a cautionary tale about using medications off label to hack your sleep. But that being said, of course, for those of you listening to this talk might be going, boy, N3 sleep's sure important in a lot of different ways. What if I took something that would increase N3 sleep? Could that reverse or change some of this? Could that have an impact on aging? And, there are medications out there that can do that. Xyrem, Xywav, and Lumryz, these are all different preparations of sodium oxybate, which is based on gamma hydroxybutyrate, which was a drug of abuse, but is being used to treat narcolepsy. Narcolepsy is that disease where people don't sleep very well and they're very sleepy during the day. And if we have them take this medication at bedtime, they're able to fall asleep and stay asleep. And there's some evidence that N3 sleep increases. So N3 sleep is also when growth hormone is secreted. So from an aging perspective, you might say, that's kind of interesting here. Let's take another look at that. But again, we haven't necessarily proven that the delta waves that you see when you take Xyrem are actually the delta waves that are generated from the brain when someone's having N3 sleep. So we need to understand that better as well if we're going to begin to take a foray into using medications and other things to try to hack our sleep or change our sleep architecture in ways that we think might be beneficial for us. So with that, I'll take your questions, and I really appreciate the opportunity to speak to the group.
Dr. Watson, thank you so much. That information is invaluable for our team here and for our clients. I'll go ahead and moderate. We've got, as you might expect, a number of questions, but I'm going to lead off with 2 questions. And actually, we've gotten a couple questions that are similar to this. One is, you mentioned the caffeine industrial complex. Well, we all know that for 30 years, there was a nicotine industrial complex, as sort of a smoking industrial complex. And, even the medical establishment for years bought into that. Smoking's fine, nothing wrong with smoking. And finally, we came around. And then, of course, we still have the alcohol industrial complex. which would have you believe that moderate alcohol is great for everything from cancer to heart disease to maybe sleep to the list goes on. And I think all of the emerging data suggests there's actually probably no safe level of alcohol, that it's actually a neurotoxin, and that probably a lot of the previously ascribed benefits to alcohol have to do with the social interaction effect. If you're someone who likes to have an occasional glass of wine, you're doing it with friends and family, you're being social. Now, that doesn't mean that you shouldn't drink alcohol, but I think we all need to be aware that the previously ascribed benefits are probably not there. My question for you is, the caffeine industrial complex, all of the now ascribed benefits to caffeine, including potentially neuroprotection and Parkinson's and a number of other neurodegenerative disease, all from observational studies. We don't know if the people, who didn't use caffeine and then went on to get Parkinson's, were they just sensitive to caffeine in the first place, or is it really neuroprotective? It's a diuretic. It causes electrolyte imbalance, can cause arrhythmias. What is your take on, caffeine for sleep? Does it help? Is it neutral? Or in all cases, is it unhelpful?
Yeah, great question. Thank you for that. I mean, so caffeine is an adenosine antagonist, just getting back to the two process model. So it kind of, fits perfectly into that. I think we accept the ubiquity of caffeine in a sense. I mean, if I was, going to design the perfect sleep environment and lifestyle for somebody, that would not, caffeine would be off the list.
Yeah.
There's no question about it. For two reasons. One is if it's taken too late in the day, it can cause insomnia. And two is that it masks the effects of sleep deprivation. And the thing about sleep is, in sleep deprivation, the sleepiness you experience is just one of the components of what sleep does for you. But sleep does so much more for you than keep you awake and alert during the day. In other words, there's this ultradian rhythm. There's the importance of the various sleep stages. There's different hormones that are secreted at different time points. It's important for memory encoding and body health. And so, you might sleep deprive yourself and kind of get away with it because you're, constantly drinking coffee throughout the day. But, there's going to be a price to pay in the long run of not getting adequate sleep. And so, caffeine is not a part of any ideal sleep schedule or sleep program that I would design.
Yeah. Well, thanks. Yeah, we obviously, I meet with a lot of our clients, and I've come to the conclusion it doesn't mean you shouldn't drink caffeine. Just like, a lot of us, occasional glass of wine is fine. But I think in some ways, I think it probably causes more harm than good. And I think people just have to be aware of that, because I think if you just, sort of believe kind of the press out there, it's great, it's good for everything, it's everywhere, it's in airports, it's it's in all these new energy drinks. But anyway, it's just something to keep in mind. Next question, and then we'll get to some of the other questions from the audience here. And actually, I had a couple of questions about this. You mentioned N1, N2, N3. I, like many of our clients on this call, Aura Ring, Apple Watch, Sleep Score. I use all three, and I've noticed that reliably I get different data from each when I use them from the same night of sleep. So my Apple Watch consistently has a lower amount of calculated deep sleep. Oura Ring is somewhere in the middle, and Sleep Score generally usually much higher amount of deep sleep. So two questions in regards to that. Is this something that your team or your research has noted that these devices may give different sort of scores? And two, this was a question from one of our audience members. Does the so-called deep sleep and core sleep, does that correspond to N2 and N3 respectively?
Yeah, so for these, we call these things consumer sleep technologies in general as a category. Some are contact that you wear, some are contactless. Some require you to turn an app on and off when you're going to bed and waking up, others don't. So there's advantages and disadvantages to all of these things. I will say in general that they're all getting better at what they do. they've all been all, I mean, most of them have been compared to wrist actigraphy, which I mentioned previously that is often used in research, which is an accelerometer worn on the wrist that measures movement. Some of them have a photic. Uh, 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 they can determine whether or not light is on in your environment. Some of them, have other aspects or other functionality, but they're all have some areas that they're more accurate than others. But the biggest challenge is differentiating wake from sleep, actually. Because as you might imagine, if you're, when you first lie down to go to bed, you're recumbent, you're quiet, you're not moving around, and yet you're still awake at that time. And some of these devices they struggle with that. They struggle to determine exactly when sleep onset occurs. So I would say for people that are interacting with those technologies, it's good, and I would consider them to be reasonably accurate kind of across the board, and encourage people to continue to learn more about their sleep through the use of these products. We get people that bring in data from these consumer sleep technologies into clinic, and we review some of that with patients and stuff, but it hasn't really been broadly accepted into clinical sleep medicine yet, although I think that that's probably going to change. Right. And then when we talk about core sleep, it's interesting when you look at these devices, they kind of talk about, wake, REM, and then deep sleep. But so they're not typically differentiating between N2 and N3 for these devices. But, for the purposes of sleep laboratory, we do. But if you, consider that N2 and N3 would make up about 70% of your night of sleep, I think it's reasonable to consider that to be your core sleep. Although, obviously REM is quite an important sleep stage as well, where dreaming occurs and there is some memory consolidation in that sleep stage.
Okay, so the deep sleep on these devices, that's not, you don't think N2 or N3, that's deep is deep, and then N2 and N3 correspond to core?
Yeah, I would say that would be the case for most of these devices.
Okay, great. Well, great. Well, we have a number of, I don't think we're going to get to all of them, but I'm just going to go through some of these questions. Could you please talk about chronic elevation of cortisol and insufficient sleep, was one of our members asking.
Yeah, I mean that, that's one of the things that sleep deprivation causes is the chronic cortisol elevation. That's a stress hormone that can have untoward impacts on cardiovascular health. So, I mean, the way that we manage, our bodies are able to manage glucose. So moving us towards like pre-diabetic type states. So, yeah, I mean, sleep deprivation is a stressful mini experiment that you do on yourself, on your body. I mean, at the same time, one night, a bad night here and there, or a short night here and there, I wouldn't get too excited about that one way or the other. We're talking about cumulative effects of short sleep here when we think about all the epidemiologic studies showing associations with these untoward health outcomes and shorter sleep. But I mean, it's just another example of there is no substitute for sleep. I mean, caffeine or wake promoting agents or stimulants, can kind of substitute for the regenerative, cognitive, perhaps, benefits of sleep. But all the other things that sleep does for your brain and your body are just going to be lost along the way. So there's no way to, there's no medication or method that I'm aware of to say, I'm going to be sleep deprived, but I'm going to, manage the cortisol related issues somehow with a medication or something that you might plan or do. So it's just the cost of doing business if you want to not listen to your body and not respect the physiologic imperative that we spend a third of our life sleeping, and you can't cheat the sleep banker on that. They're keeping a close tally.
Right. Great. Not surprisingly, we got actually multiple questions about melatonin, both as a sort of regular sleep aid and also as a travel aid to be used only occasionally.
Yeah, melatonin, in sleep medicine, it's mostly used and thought to be effective to treat what we call circadian rhythm sleep disorders. So these are people, for instance, that may have delayed sleep phase syndrome, where they naturally desire a much later bedtime and wake time than is kind of socially appropriate as far as typical work schedules are concerned. And so in those individuals, we would often advance their sleep schedule by exposing them to light in the morning and melatonin a couple of hours before intended bedtime at night. When you think about melatonin as a soporific agent, or to take it as a sedative hypnotic, there's some people feel that it helps them, others it doesn't have much of an effect. There's a lot of debate about when to take it. I mean, in generally speaking, when we use it from a circadian perspective, we give it hours before intended bedtime, and most of the time that probably is how it should be taken, even if you're using it to try to help you to fall asleep. um, One thing about melatonin is, first of all, it's not FDA approved for anything, so you're never absolutely certain, how much melatonin you're getting in any preparation that you might buy over the counter. But what we know is that people need, if they take melatonin to try to help them fall asleep or for circadian issues, you don't need anywhere near as much as what most people take. 1 milligram should be plenty. We see people taking 5, 10 milligrams of it, and it's unnecessary in generally speaking when you look at the literature. So, I think that there are instances where melatonin can be helpful, where it can help facilitate sleep in some individuals. That the data is a little bit all over the place, but I do know I've had many patients feel that it really does help them. So in those instances, go for it, but I'd go with 1 milligram, and I'd probably take it a couple hours before my intended bedtime.
Great. Well, a few more questions here. I think we're slated till 5. We might go a little bit over. Dr. Watson, are you able to go 5 minutes over, or?
Yeah, sure.
Okay, great. Just a couple more questions. A couple questions about this. The correlation you showed between obesity and minimal sleep and other neurodegenerative diseases. How strong is the data that those are causative rather than sort of associations? Maybe you could comment on that.
Yes, thank you for that question. For obesity, it's we got good data. So we know that when you sleep, there's two key hormones in your body. There's a gut-derived hormone called ghrelin that tells you you're hungry, and there's a fat-derived hormone called leptin that tells you you're full. And we know that when people sleep deprive themselves, they become leptin resistant, and ghrelin levels are impacted as well. And people crave high-fat, high-carbohydrate type comfort foods on top of it all. So there's good physiology showing that sleep deprivation impacts the hormonal milieu inside the body to foster an obesogenic type of state. And so that's pretty well established. As far as neurodegenerative diseases are concerned, it's really interesting discussion is this kind of pejorative notion about sleeping pills. And I mean, we could spend a whole hour talking about why they have such a negative connotation associated with them. But let me just put this out there for people that say, oh, I don't want to take a sleeping pill because I don't want to develop Alzheimer's disease or some other neurodegenerative condition. My sense in looking at the literature is that the medication is at the scene of the crime, but it didn't commit the crime. Okay. I think that, healthy people with healthy sleep, or people that are devoid of sleep problems, don't take sedative hypnotic medications. Only people that are having difficulties do. And I think it's the sleep difficulties, and it's the shorter sleep and the sleep impairment over long periods of time that may contribute to the development of neurodegenerative disease. Now, look, there's no randomized double-blind longitudinal study looking at sleeping pills versus no sleeping pills in the development of neurodegenerative disease. So we have to be very cautious when we talk about this in regards to these medications. But for people that struggle with insomnia, I mean, I would be more focused on improving my sleep than I would on the problems with the tools that I'm using to do that. And one last thing is that there's a whole new class of medications that blunt the wakefulness drive. They're called dual orexin receptor antagonists, or DORAs. There's 3 medications in that class now that look to be very effective at treating insomnia and improving daytime symptoms, and don't maybe have all the baggage and everything that some of the other benzodiazepines and things like that, or the Z drugs that seem to have. So biomedical research moves forward. We have new tools at our disposal, and so for anybody struggling at that, they're called DORAs, DORAS, dual orexin receptor antagonists. And you may have heard me say earlier, orexin is a neuropeptide deficient in narcolepsy. So they leveraged our understanding of that neuropeptide in narcolepsy to develop these effective medications for insomnia.
Yeah. Well, no, thank you so much for that. We had multiple questions about that. And I know in our own practice here, and you and I spoke about this when we spoke several weeks ago, getting to the root cause of disease is so fundamental to what we do as a precision medicine clinic. And, for high cholesterol, well, yeah, you can paper it over by taking a statin. But if you really get down to it, what is the cause of the high cholesterol? Let's address that. What is the cause of the poor sleep? Is it insulin resistance? Is it inflammation? Is it, decreased mitochondrial efficiency? Or a whole host of other chronic diseases. And I think our bet is your bet as well. Let's try and address those before we reflexively go to benzodiazepine or an Ambien or something else. So, okay, great. One last question, and this, I suppose, is drawing on your neurology hat, maybe not as much your sleep medicine hat, but how do we boost lymphatic flow outside of better sleep and reduce the vicious cycle?
Yeah, that's the $100 million question, isn't it?
Right. Right.
There have been a lot of devices that have been developed that monitor the EEG. There's one, I think one's called Sleep Shepherd. But it turns out that if you introduce tones of a certain frequency into each ear bilaterally that are different in a slightly different frequency, that can link up with the EEG and ostensibly kind of shepherd the EEG to certain sleep stages. Now, I haven't seen a whole lot of data beyond what people have said around that, and I'm not sure that even works. But there's some stuff out there related to that would be non-medicinal and possibly a way to increase it. Beyond that, I think, living the healthy lifestyle and getting regular exercise, prioritizing your sleep, all those things would be really important. But I am, quite intrigued by the notion. I mean, I put the Michael Jackson thing in there just to stimulate thought a little bit. But I must admit, when I think about these medications, the oxybates, and certainly there are other medications too, mirtazapine and trazodone and some other things that might increase N3 a little bit. At some point, I think certainly an entity such as yourself in human longevity, when you're thinking about kind of ways to change things, as we understand these medications better, if we conclude that the N3 or the delta waves that we see during sleep that are fostered by this are actually the delta waves of sleep, which all those questions are unanswered right now. There may be opportunities to increase N3, but other than that, I mean, it's a problem in aging because it does go down as we get older. And as I mentioned, growth hormone is secreted in that sleep stage, and growth hormone is obviously a factor related to healthy aging as well. So it's a great question. I wish I had a better answer, but I think companies like Human Longevity, the work that they're doing, and certainly the biomedical research enterprise in sleep medicine has their eye on this, and certainly hopefully we can find ways to leverage either technology or medications in the future to increase N3 sleep, because I do think that would benefit human longevity.
Great. Well, Dr. Watson, again, on behalf of our entire client base and ecosystem and our team here, we are so grateful for your time. I know you're extremely busy, and this has been extremely illuminating. I hope everyone gets some wonderful sleep tonight. Thank you very much.
You're welcome. My pleasure. Take care, everybody.